Okay, in this video segment, I will discuss the procedure behind doing a path plot in the 3D Experience Release 2022x. Uh, I will do that in the context of an example, and the example that I will take into account is a solid disk that's rotating at a constant angular speed. The idea behind path plot is you specify a certain path in your model, and you will be asking CATIA, not CATIA, sorry, 3D Experience to plot certain entities that were calculated, such as von Mises stress, displacement, anything that can be obtained from the finite element results in 3D Experience uh, can be plotted on that path. Okay. So the specifics of the problem are here. We have a disk which is 300 millimeter in radius and a thickness of 16 millimeter, uh, turning at a constant speed. Here is the radius of the disk, 300 millimeter, angular speed, which is 1,000 radians per second, around 10,000 RPM, basically. Young's modulus and Poisson ratio of steel, and the density of steel, which is almost 8,000 kilogram per meter cube. Now, the reason that I want to do this is that there are analytical solutions available for this problem. What you see here are the radial stress and the hoop stress given in terms of distance from the center of the rotation, and this is the radial displacement as a function of radius. Okay. Now, if you look at these results, you actually will see that the radial and hoop stress are at the center of the disk are maximum. I just wrote the radial one here, and then obviously the radial stress is going to drop to zero at the periphery, but the hoop stress is going to be maximum at the outermost boundary of the circle. Okay. So these are the results that are predicted by these formulas, and we're going to be checking our FEA calculations against those. Here is the plot of the radial and hoop stresses. These are, by the way, principal stresses, as you know, and this is the result for displacement. Zero displacement at the center of the disk, and maximum displacement very close to the end. Okay, very close to the end. Right. So this is what we're going to be doing. And once again, the purpose of these videos is for people who want to use the FEA solver of 3D Experience to be able to do certain things that are not widely available on internet or on YouTube, for example. It's tough to try to figure this out just by yourself. It's going to be, you have to spend a lot of time. So this is to help those people. Okay, incidentally, because of the symmetry, I can take any sector of this circle. So I'm going to take a 45-degree sector. And then once again, because of symmetry, I don't have to use the model entire thickness of this disk. I'm going to use half of it. Okay. So keep that in mind. Okay. So let's go here. Here is a part. So let me rename this thing to be called uh, path plot. Path plot, just so that I can remember what it is if I ever look for it. There we are. So on this plane, on the let's say on the XY plane, I will sketch. Okay, sketch an arc. Okay, let's close it. This is a 45. This is going to be a 45-degree sector. Do another one. Let's dimension it. Dimension this angle. Actually, that's the radius. Let's do this 300 millimeter or 0.3 meter. Okay, and the angle between this line and this, we take 45 degrees. It can be any sector, but that's what I'm doing. Okay, so good. Exit. Okay, now we're going to be padding this thing up by half the thickness of the, the disc. The thickness of the disc was 16 millimeters, so half of that is going to be 8 millimeters. 8 millimeter. There we are. And we say OK. Let's create some material here. So we go to Tools, Create a Material. I'll call it Path Plot. Path Plot. And notice that simulation domain is checked, which is good. Okay, so this is going to be created. If we can't find it here, let me refresh this. It should be the one on the top of the list. Try it again. I thought a modification date. There we are. Okay, so right click, apply. I'm going to kill this. Apply there. There we are, path plot. Now we're going to input the values. Okay, so it's structural, general density 7,850, 785. Those are density. Okay, let's go to Abacus Multiphysics, mechanical, elasticity, elastic, and this was 200 gigapascal. 200 gigapascal, and Poisson ratio 0.29. Okay, that's all we need. All right. Now we're going to go to structural model creation for meshing purposes. Standard model, standard. Now I'm going to use the I'm going to use a sweep mesh. Now I can use tetrahedral one, but because this was a pad region, it's very amenable to sweep. So I'm going to make it sweep. So it's going to be hex elements throughout. And as far as the size goes, I'll leave it like this. If necessary, I'm going to change it. I'm going to make 2 layers. So basically, this is half of the thickness of the disk, 2 layers of elements through it. And I put this number here. I'm not sure whether that's too fine or too coarse. We'll see that. So update. Yeah, that's too fine. You can see that. Just look at this. No, I don't want that. Where is the mesh here? I'll do it until we are reasonably happy with it. So let me actually make this thing instead of maybe let's make it 20 millimeters. We'll see how it goes. actually 10 millimeters. We'll see it. Yeah, that's more reasonable. Okay, you say fine. Notice that we have two layers of element through the thickness. I didn't want to use the tetrahedral element, so I used the sweep feature, and that's good enough. Okay, so first of all, let's save this. All right, and then we're going to go to, oh, one thing I want to do, because I would like to specify the axis of rotation here uh, later on when I specify the angular speed, you need a line there. So instead of doing that, I'm going to create an axis system here. So let's go to, let's go back to the model. Uh, let's go to our part. It can be done later on too, but rather do it now. Okay, so I went to my part design, basically model or essentials. Here's axis system. See that axis system, and right there it creates an axis system at the global origin, and I'm going to be using right. It's right there. You can see that right there. Okay, yeah, see right there. I'm going to use that later on for specifying rotation. All right, let's go. Let's go now in uh, uh, structural scenario creation. Yep, we're going to be doing. We're going to use this model that we just created. Okay. Now, setup. Sorry, procedure. We're going to do static step. As a matter of fact, static step, that's fine, but I don't really need to do the nonlinear problem. So do not include the geometric nonlinearity, because the solution that I presented to you at the beginning of the video, they're all based on linear elasticity. So I just deactivated this include geometric nonlinearity. Okay. All right. So now we're going to specify our restraint. So we go to restraints. Now, notice that the sides are planes of symmetry and the bottom are plane of symmetry. So we go to here, plane of symmetry. Let's start. You cannot do multiple selection. At least I couldn't do it, so I don't know. So I'll do this one. There is one plane of symmetry. Turn it around. See, when I try to select another one, I don't think control works either. Yeah. So, okay. Let's do another one. Although I could have created a group of elements and applied that probably on the group, but that's okay. This is simple enough. We can do that one by one. Here's the second one, and the bottom. These are all planes of symmetry. Okay, very good. As far as the load is concerned, it is centrifugal force right there. You can see that. The support is the entire model, the whole model, part body or the whole model. The axis of rotation is the z-axis right there. See that? Remember, I created the coordinate system here. That was because I wanted to select its z-axis for axis of rotation. You can see that. And the value, this is RPM. So let me make this thing 1000 rad underscore or rad per second, okay, which is about 10,000 RPM. Yeah, right there. And we say, okay. All right. It could be, now I'm not sure, it could be that instead of the z-axis here, you could have selected this edge too. So the z-axis may have been just unnecessary. But in the event, for example, there was a hole here in the middle, it was not a solid disk, then the edge will not be able to pick, but this coordinate system that you created would have been okay. That's pretty much it. We don't need anything else. So let's go ahead and run it and see how it works. So we go to simulate. Let's do a model check first. As I've been saying all along, it's a good idea to go through these two checkers. So if there are any obvious things that are going to pop up right now in these two steps, we can fix it. So far, everything that I've done is totally unrelated to what I actually want to show you, namely path plot. But we wanted to do it in the context of an example, and this is our example. Okay, we'll get to the path plot in just a couple of minutes. I prefer to do it this way so that it's not a concept in abstract. Doing it to you, doing it and showing it to you with a live example. Okay, it's going to be done. Good. And now we're going to run. This is the run step. Okay. If this is done the way it's supposed to be, you're going to have biggest stress at the center, red at the center area, and then gradually drops to lower values on the periphery. But as far as displacement goes, displacement is maximum with the periphery and zero at the center. So we're going to check those before actually we create our path plot, which is the focus of this presentation. Okay, extracting results. Very good. Okay, so if you look at what we've got here, this is the initial step, initial increment. This is the von Mises stress at the final deformation. Okay, and biggest in the middle, lowest at the periphery, and its circular pattern, which is confirming what we said about symmetry. All right, and as far as displacement goes, it's going to be the other way around, biggest on the periphery and zero at the center, basically. Okay, so let's do the following. Let's go back to the, yeah, this is fine. Now, notice that here, right here, it says XY plot from a path, right there. But if you go to setup, you will also see that you can actually create path here. So there's two ways to do it. You can create the path right there, or if you didn't do it here, you can do it on the fly when you go to plots, and you can do XY plot from path. The choice is yours. It really doesn't matter. So what I will do is actually I'm going to go here. I'm going to go create my path first. So let's see now in the setup, there's a path. Okay, this opens up, and notice that first of all, down below, there is this little icon which says show or hide the mesh. And the reason you may want to mesh the mesh, it could be that you want to create a path between certain nodes, for example. But let me show you. Here's the mesh. Okay, now when it comes to doing path, I'm going to do two of them for you. One of them, notice that path can be created based on selecting nodes or selecting geometric edges. So I'll do two, one based on selecting node, one based on selecting geometry. Let's start with geometric edge. I'm going to give this thing a name. I'll say bottom edge. Okay, now, so all I have to do is to go and select this line. See that? The bottom edge. And notice that this line is along the y-axis, this line. So I created one path, okay, and in the model, geometric model, it's something which is number 31. I don't know. It really doesn't matter. Okay, and we say apply. Created one path. Let's do another one. This one is going to be based on nodes. at the bottom nose, at the bottom edge. Okay, so I'm going to change that thing to nodes. Now I can select nodes, the nodes that I want the path to be plotted against. For example, I can select this node right there. I can select this node. I can select this node and that node. If you want, you can select all of these. You could have put it in a group and then probably selected group, but it doesn't matter. So on purpose, I'm not going to do all of these. I'll do another one right there. See this? And I'll do another one right there. And another one down, I don't know, maybe here and there. So I have two paths basically. We say, okay. So notice that in the results for the tree, I have created two paths. You can always get to it. If I double click on this, for example, notice that it shows you the path we create. That one was this, okay? If you go to this one, it's the node that you created, right? The path from the nodes that you created. And you can delete anything you want. You can add stuff. But anyway, so let's move on. All we did here was to create path. So now we're going to go to plots, and we can go here, XY plots from path. Notice that even if I had not done it before, I could have added stuff there. See that? I could have added more path, but I created two, and they're right there. So let's start with the bottom, the one at the bottom edge. Okay, good. Now we come to that true value in a minute. And what do we want to do? We want to plot the stress. Okay, so we don't want translation. We want stress components. And for example, we want the maximum principal stress. Maximum principal stress is actually one of those stresses that we had. You remember there was a radial and there was a uh, uh, radial and hoop. Okay, so let's do the maximum principal stress. Okay, all right, and you got everything here. Maximum principal stress, and then we say apply. Okay, so the only thing is that if I wanted to look like this, if I wanted to look like that, notice that these are going down. So instead of true distance, let me try y distance. Apply. Or coordinate. Apply. Right there. Incidentally, notice that it says there is a checkbox here which says deactivate existing XY plot. So let me do that. Apply. There we are. So this is the one of these two stresses. Let's try the other one, intermediate principal stress, mid principal stress. Apply. What did I do here? Mid principal. The first one, oh yeah, I did not want to deactivate the other one. So okay, let me see now. So this is the middle one, and let's also do the. Uh, you don't want to deactivate these, okay? So we go here to I uncheck that, okay? This was the middle one. Let's do the first one that I did, which was maximum. Apply right there, okay? So this one that goes to 0 is the radial stress. This one, which does not go to 0, is the hoop stress. And notice that they are the same at the center, as I told you. Now you can also do the von Mises stress, for example. If you want, you can do von Mises stress, except that you don't select the principal one, you want Mises. Or if you say the lowest one, minimum, of course you're gonna get you zero, because there is no stress through the thickness of the disk. And just to confirm that here, minimum principal stress, apply, it's right there. You can see that zero. Now let's also do so this agrees perfectly with that plot. Let's do the displacement. Okay, so we say okay here. Okay, all right. So let's see what happened. This was based on, remember, we created some plots here. They're right here. See that? So this last one, if you see, right there. This is the last one that we did. Any other stuff that we don't need, we can delete. So let me close that. Let me clean this up. Okay, so let's go clean it up. Anything that we don't want, you might as well delete. These things, we don't want it. We actually, I need the last three, right? So delete these. Let's check it out. Apply. One of them I may have inadvertently deleted. So let's see now, what do we got here? Let's do the following. So delete these one more time. I'm going to go through it again. Okay, so let's try it. We have the path. We don't have the plots. We deleted them. Let's try again. We go here, bottom edge, y coordinate, okay? Because it is along y, that path that I took is along y. And I could have done the true length too, but it would not look like that. It would look, going like so. All right, let's try it. Stress. This is a review one more time. So we go to maximum principal stress and do not deactivate. Okay, apply. Very good. That's one. And then we're going to go to medium principal stress. Apply. That's the other one. Okay. These are the two that we created. And we're going to say okay. Close this. Close that. If you ever want, you go to this last one. Apply. And there we are. Okay, so everything is there. Now, you might say, okay, what about this other plot that I created? So let's try it. Let's try it on this. We go and select for the path the other one, nodes bottom edge. Once again, y coordinate. Once again, stress, but I want the maximum. Apply. You might say, well, wait a minute, what happened here? Why does it look like this? Remember, I did not pick all the nodes. I did not pick all the nodes. Initially, I took the nodes, the first 5, 6 nodes, consecutive nodes, and then I made a jump, and then I made a big jump to the end. So actually, you can see that although this is a line, it's deceiving because it is showing you the value that the node matching the curve that I had. Okay, so that was my point. Is bottom edge. Yeah. So let's go ahead and plot the displacements. How about that? So let's clean all of this. Don't need it. Close it. And one more time, you click on the XY plot from path, translation, okay, magnitude. We can say magnitude, or we can say in the direction, in the appropriate direction. Magnitude, because there is no displacement sideways or up and down, so it's going to give you what you want. On the bottom edge, okay, to distance, but make it y coordinate. There. This this is that curve. Okay. Pretty much it. Okay. Good luck.